Focus. You there? Can you handle this? No, you're an old camera. So, not sure where to even begin. So, sure hope I'm in focus. I've never done this before. This is very awkward for me. But I wanted to take a minute and say nothing. Hey guys, my name is Kevin. Wanted to take a minute, introduce myself. I'm not very good at this. I'm new to this. It's awkward talking to a camera by myself in my garage. But if I can do it, you can too. Just want to take a minute and say I was invited tonight to go to a car meet. It was kind of like a pit stop for a cannonball run, and kind of got some bad information. Turned out to be a pretty cool experience though. I was really debating going or not based on the information. Turns out what happened, there was a rain delay in Georgia, and last night of the races that held them up apparently for their schedule today. They're supposed to all show up around 8 to 12 at Scorpion Performance as a pit stop, get some refreshments and snacks, and we're going to go there and check out some cars. But there's nobody there. But this guy named Zach was super cool. Gave us an entire tour of the facility. We're going to check that out here in a minute. But I just wanted to say, being new to this, if anyone out there is new, get up, go out, do something, go get some content. You never know what's going to happen. I went under the impression that I was going to get some car video tonight and ended up getting a full tour of a performance shop. The whole fabrication process is not the best quality. It was spontaneous. I was not prepared for it, but I'm going to give you what I got, and I'm going to keep getting better at this. Thanks.
I'm Zach Collins. I am the Chief Operating Officer of Scorpion Racing Products here in Ocala, Florida, in charge of new product development, R&D, and engineering, and some operational management as well. And so you'll see a mix, all the pictures in here and everything, obviously pretty much half and half. Half are all import related for all of the engine transmission mounts and chassis and suspension components that Innovative Mounts manufactures. The other half are domestic applications and some of the offshore powerboat stuff that Scorpion rocker arms and valve train components are in the powertrain of. So we've been here since 2011. This is basically since 2 years ago, we moved Innovative Mounts down from Charlotte, North Carolina, our sister company. We're ISO certified. We have a federal firearms license. We process federal firearms components. A lot of that does travel over to the manufacturing side from the anodizing side. We do anodizing for not only our own rocker arms and our own mount suspension components. We also do it for medical device manufacturing companies. We do it for aerospace and defense contractors. We've worked with the University of Florida on satellite components and some of their SAE teams for their submersible vehicles and their Formula SAE race cars. We also do it for one-off customers off the street, somebody who might be restoring a 1970 audio equipment and they want it to look brand new again, we'll do that. We do a lot of one-off, engine components or race car parts, whether it be a fuel tank or trim pieces, things like that. So that's really how a lot of people first find out about us, and then we also do contract manufacturing work as well. So some of those same customers, aerospace, defense, medical device, will come in to audit us to make sure our processes are, fully controlled as far as quality goes. And then they'll notice we have manufacturing capability and ask us to quote that as well. So we machine materials here, everything from stainless steel, alloy steel, aluminum, brass, Inconel, super alloys, tool steel. If it is a good fit for our processes and our equipment, we will quote it and try to get the business. So we'll start, if we want, we'll start down here at the end of the shop in our R&D area. It's a multi-purpose R&D area for both companies. So a little bit of innovative mounts and a little bit of Scorpion as well. These are all the front offices where all of our administrative staff stay, whether it be sales, marketing, operational management, applications engineers, design engineers. In here is where Tyler, our engineer for innovative mounts, sits. He's got his 3D printer. He's got a lot of prototypes there. Obviously his workstation with his computers. He does a lot of CAD and design work. He also does tech support for all of our customers as well. And then we have our Director of Operations, Kate Weaver, on the Scorpion side. We have Jessica Weaver, who is also our administrator for all the companies. So basically she's the boss lady. She does HR, she does purchasing, she does operational management, everything. She also oversees Raymond's powder coating across town as well. So back here is the R&D area. This is where the magic happens and all the fun stuff takes place, from prototyping to product validations and testing. So obviously multi-purpose area. I apologize, it's probably a little rough in here, it smells like race fuel. So this is, obviously you can see over there, turbos, for one for the S2000 over there. And then we have the V16 in the CRX right now with the all-wheel drive conversion, sort of halfway in progress. We have spare parts all over the place as well. So this is going to be all-wheel drive for a drag race application. The S2000 will be a track car for Sebring, the Firm, Road Atlanta, all the tracks like that. They will both be company cars to show off and showcase all of the innovative mounts products. We also have test engines as well. So this is an LS3 or L92 GM engine here. This is one of our show engines. So these are our aluminum pedestal mount rocker arms. We also have our fuel rail kit on here as well. We make fuel rail kits for LS1, LS2, LS6, LS3, L92, and LS7 as well. Several different engines, whether they're donor engines just for fitment, spares for blocks for the Spintron, or takeoffs out of the field from customers. This is all 100% done in-house on both sides of the fence for Innovative and Scorpion. All the manufacturing is 100% under this roof. The only thing we don't do in-house here, if it's powder coating, obviously it goes across town to Raymond's for powder coating. If it's heat treat, our steel components either go to Daytona Beach or Atlanta, depending on the process that's required for heat treatment or cryogenic treatment. Everything else is done 100% here under this roof. So that's one of our display engines. They have two different heads on them, the Trick Flow Gen X 255 and the AFR Renegade, more popular applications. And then we also have test engines over here, quite a few cylinder heads for rocker arm fitment. This is a Chrysler Big Block Mopar 440. This is a small one, it's like a Gen 1 old school small block Chevrolet. This is actually made for the Spintron, which is pretty much like a valve train dyno. So when you set up an engine for the Spintron, it's not a running engine. It doesn't have connecting rods, it doesn't have pistons, it doesn't have a conventional crankshaft. It has a straight shaft that's a mandrel in place of the crankshaft, and you couple that to a 50-horse electric motor, which is controlled by a variable frequency drive and software that you program it. And you can control the RPM of that motor, so it'll actually rev up and decelerate the engine at whatever rates and whatever time periods you want. So that way you can duplicate real-world applications. So we can do like a drag race application where you do a warm-up, you do a burnout, you stage, you do a quarter-mile pass, you come back, you do it again. We could do that an infinite number of times back to back to back. We could do 50 laps at the half-mile dirt track at Eldora. We could do 20 laps at Bubba Raceway Park. We could do the Daytona 500. We could do the Rolex 24. We could do an offshore boat racing application and duplicate that RPM cycling that those applications see in the real world. We put bore plugs in the cylinder bore so that way it keeps the oil contained to the bottom end. All of the engines we put on the Spintron are dry sump oiling systems, so there are some modifications we have to make to the oiling. Obviously here's some more test engines as well. This is a 77 Vega drag car. It runs NHRA Super Gas or Super Pro, which is like an electronics category of bracket racing or index racing. 468 big block Chevy, still got iron heads, it has a GM Powerglide transmission, 12 volt rear end, 430 gear. Runs 6.0s in the 8th mile like 115 miles an hour, and run 950s in the quarter at about 145. And here is the actual Spintron room itself. So there is some neat stuff that goes on in here as well. So this is where most of the engine components, most of the R&D, any of the donor components or prototypes are getting ready for testing are housed. So in here we have the Spintron itself and several engine components as well. So you'll see the Spintron itself, and I'm going to make it more accessible for you. So as I mentioned, the Spintron is basically like a valve train dyno. So we have a couple tools that help us analyze how valve train parts are performing and the valve train is working as a whole. So we have high-speed cameras. We also have a laser, which is basically just like a displacement sensor that tracks the valve motion. So we cut a hole in the side of the cylinder wall, put a laser in that cylinder, and have it oriented at the valve so it actually tracks the displacement of the valve. So we can actually take a low RPM curve where everything's comfortable, stable, happy, and in control, and then we run it at high RPM and we overlay those two curves and we see where things are getting out of control, whether there's any deflection in the system, there's loft over the nose, where things are coming off the cam lobe and then rebounding back down onto the cam lobe, bouncing as they make contact again on the closing ramp of the cam, to see where things are out of control. Or we can use it simply as a cycling tool. So we can say, okay, we're going to run this thing 5,000 RPM for 20 days and see what the parts look like after X amount of million cycles to see what the wear looks like. What's going to wear first? How rapidly do things wear? And at the same time, we can use this for side-by-side testing for our own products versus competitor X, or we can use it to validate products for a lot of our private label customers. We do a lot of work with the big OEs, whether it be marine or on land vehicles. And we also do a lot of private label manufacturing for our own competitors as well. So we actually make more aluminum stud-mounted rocker arms than any other company in the country. So we make anywhere between, depending on the year, depending on how far back you want to go or what sample you want to pull, we make anywhere between 300 to 400,000 rocker arms a year. So this is actually the Spintron test rig here. As I said, dry sump oiling here. You have the software that you program that will control the variable frequency drive that controls the 50 horse electric motor. It's coupled to the mandrel in here. Mandrel is just a straight shaft, again, no counterweights because there's no rotating assembly, so there's no pistons or connecting rods. You have that counterweight for it. And then that's with a drive coupler connected to the 50 horse motor, and that's what spins the engine itself. It's surprising to most people who haven't seen it or heard it before. It's very loud. You would think, being that it's just rotating and there's not much stuff moving around, from the friction and the metal-to-metal contact, what you actually hear in the exhaust of a running engine, only about 55% of that is the sound of the combustion. The other 45% is actually the sound of moving parts. So this is about half as loud as an engine with open headers. So it's actually pretty impressive and pretty surprising at the same time the first time you're experienced or exposed to it. In here are just various parts and pieces for several of the test engines. And then over here, some of the data acquisition. So this is actually one of the cycles that we've run. So you can see in this sample file, we look not only, here is the RPM graph. So we ran it at 1,000 RPM for the baseline. Then we ramped it up to 8,000 RPM and then a controlled ramp slope down. So here we have the valve lift. So that's what the curve looks like. So basically that's the valve motion. So that would basically be a little bit larger, obviously, because you have the rocker ratio multiplying it at the valve as what you would have on the cam lobe. But this should duplicate the same profile of the camshaft lobe. So here you can see it opens, goes to max lift, and closes as well. But then down here, as you zoom in, you can also see at high RPM how different the two curves are, to where your ideal curve and your actual valve motion have a little bit of difference in them. So you look at those deltas and see how much things are moving in the system. Obviously, the closer you can get those curves, the more controlled everything is in the valve train. Here you have the valve velocity, obviously just change in displacement over time. Then you have the valve acceleration, change in velocity over time. And we also measure the jerk with this, which is the change in the acceleration over time, basically the fourth integral there. So then you look here, We have a bunch of variables here that I can plot and chart out as well. Here we just have a tach that goes in line with the RPM curve of the cycle. You can see here we maxed out about 8,008 RPM. And then you can see at high RPM how much of a delta or a difference there is between those two curves and how rough it looks in some of those areas. And that's how out of control things are not moving in a smooth curve. They're bouncing, they're deflecting, sometimes they get unhappy. And you can do this to improve parts, you can do it just to cycle parts. And basically there's two main goals in valve train engineering because when the valve train gets out of control, it robs you of horsepower, so there's horsepower potential left on the table, and it also kills parts. The more things are moving around and the more mass you have in the system, the more valve spring pressure you have to put on it, the harder it is to control. But obviously, the more spring pressure you put on it, the more load and stress you're putting on all the other components in the system. So there's a compromise there, and you have to find a happy medium to where you can optimize everything to make it work as efficiently as possible. So that's everything that goes on in here, and then we'll go back out to the area here. Outside of R&D, there's one other operation that's performed here. Innovative Mounts does make all of their own bushings in-house. So for all of the engine mounts and transmission mounts, a variety of applications. So we have different durometer values that we make the bushings. So somebody might have a daily driver, they want to ride like a Cadillac. They want a lot of dampening to happen in the mount itself, so that way it absorbs all the vibration from the road, so that way it's a nice smooth ride. So we have very soft bushings for that application, or we even make solid steel bushings for drag race applications where you want all the torque transfer and you don't want the mount to absorb any of it, because then obviously you have a power and torque loss through the drivetrain itself. So that's what we do over here. We actually pour our own urethane bushings. We have more engines over here. These are basically a combination. This is an old school Hemi, Chrysler Hemi, that's been retrofitted for the Spintron as well. And then we have a couple big block Fords, a big block Chevy. These are also used for quality control, measuring the ratio of the rocker arms, making sure the part measures correctly on the engine as it should. And then we'll come out here. And this is the innovative mount side on the steel fabrication side. We also do contract manufacturing on this side as well. So you'll see saw cutting operation where raw material will begin its life within the building. Some raw material does not get cut. We also get raw material in sheets, which is for the laser cutting operation. But we have steel tubing, aluminum billet, a variety of materials that'll start and get cut into whatever length they're supposed to be worked through. And then we have several fabrication and weld cells as well, mostly MIG welding. These cells here are dedicated primarily to contract manufacturing work, non-innovative mounts related components. Then we have work in process here. We do a lot of bolt-on accessories for other companies as well. So they'll start here, they'll get cut on the laser like these flat pieces. Then they go to our press brake where they get bent, and then they come over to the weld cell and get welded together. And then they'll get ground and smoothed out, and then they go across town to get powder coated, and they come back in, and they're ready for final inspection and packing. So then in the center of the shop, you'll be able to see on the other side. I'll flip on the other lights real quick. So this is our, the best view is actually over here in the center. This is actually our Mitsubishi laser. They go two lasers carbon dioxide. You can see here, it's got a sheet, so we have that way parts don't fall through, especially small parts that fall through because it's being created by the sheet itself. So this can cut stainless steel, aluminum, mild steel. We use to cut quite a few different various materials. We don't actually have allocated, so once it's done with a cut sheet, we'll swap the raw sheet in for a fresh program, and then take the cut parts out, and we just manually remove the parts out, remove the scrap. And from here they go over to the Amada press brake if they need to have any bends into the part, and then from there they go into our 4 MIG cells against the wall over here. All the cells against this wall are dedicated to the Innovative Mounts product. And Innovative Mounts has 2 configurations of the engine and transmission mount. For every steel fabricated part number that's available, there's a CNC billet aluminum part available as well. The billet aluminum costs a little bit more because of the process and material, but there are some advantages to that as well. All the raw material in sheet form that comes in, we have some aluminum as well because we do some contract manufacturing cutting for others in various industries. So as we walk through, now we'll get into the CNC operations. I apologize, the dust collector for the laser never takes a break and it gets loud sometimes. What that's doing is it's pulsing air across the filters that collect all the dust from the laser cutting, and it shakes them so that way there's a collection at the bottom so the filters don't stay saturated with particles. So this is the heart of our operations, our CNC shop. We have 6 of these Swiss turn. They're actually Scca, it's the brand that we use. Swiss turn CNC lathes. They're called Swiss turn because when they were first developed, they were made to make really small, precise, tight tolerance parts, like Swiss block parts. So we use them to make all the steel components in our rocker arms. Trunnions, pins, rollers, push rods, seats, shafts. That all comes out of these machines. The machines over here to the left. These are the newest pieces of CNC equipment in the building. These are Tucson TT2100 twin turret lathes. So we actually take our rocker arm extrusion that you can see is already shaped like a rocker. We don't machine it from a rectangular or round billet. This gives us multiple advantages. 1 being there's less scrap, 2 less machine time required, and 3 better mechanical properties than machining it from a billet, because whenever you're machining a metal, you're introducing stress into that and you're altering the grain structure on the surface, where this is already formed that way, it's tempered in that shape. It's much better mechanical properties than it would be when machining from a billet. So they put the center 12-foot bar material into the bar feeder. It auto feeds into the machine. The first time the operator touches the part, it's fully machined, it's ready for inspection and deburring. That's what's taking place here. Everything, as I mentioned, is the end of second shift, so everything's idle right now. Then we have our quality control department. That's where we'll have all of our micrometers, calipers, dial indicators, dial bore gauges, thread gauges, go-no-go gauges, optical comparators to measure angles or radiuses or radii. And that's all taking place in that room. And then we have our VF2 cell, which is a series of hot VF2 mills. There's multiple operations taking place in here. We have fraction and fire capabilities. So we'll do some contract machine work in here. This is here you can see actually running the board now. So we get it now. So we do some changes here. So the operator will transfer the work from station to station. So then we 3-axis, and then we have a 5-axis machine here, which is dedicated to the rock roller machine. So we'll actually have a saw cut length out of that rock roller extrusion, and we'll fixture it on the front table here. And you see the first side, the operator will flip it against the left, the second side, and then the small machine. So this is a full 5-axis. We have X, Y, and Z, as well as A, and then these chucks can independently rotate on the B axis as well, so full 5-axis simultaneous machining. And then we have one machine that we use for all of our shaft rocker stands. It's pre-hardened steel. If you use just a regular steel that's not pre-hardened, again, you're stressing the material. Once you unclamp it, it'll bow and twist up like crazy because you stressed it so much because there's so much material removal. At the same time, you can't machine the part and then heat treat it afterward without some warpage and distortion. So then there'd be additional machining operations required to get all those surfaces back truly flat and in the orientation they need to be. So that's all tooled up for pre-hardened steel, which is completely different than the tooling for the aluminum that you see in the other machines. This is a 3-axis R&D machine here. We're making some of the CT bore plugs for the Vintron. So this is actually a bottom, and the top has countersunk holes in it. And then when these are done, they'll both have really big 45-degree chamfers in the middle. We'll have a really large rubber O-ring material in between them. And when you tighten them, they push the O-ring out against the cylinder wall and seal against the bore. And that keeps all the oil retained down in the bottom end of the engine. So that's just for oil retention. So since Vintron has no support and isn't around anymore, we have to do what we need to do to support our own Vintron cylinders. So this is a prototype rocker we've actually made out of billet. You can see the machine finish on the surface versus the extrusion. We'll make a couple prototypes out of billet to make sure the process is correct. When you're extruding material, there's a die charge. They have to build the die that pushes the material through that shape and comes out the shape you want it. And then at the same time, there's also a minimum order requirement, normally in pounds. Ours normally at most suppliers is 1,000 pounds. So obviously you want to prove out that that's the final shape you're going to use before you invest more in it to make it permanent. Obviously that tooling is very costly. All of our material comes from the U.S. We have 3 sources for the aluminum, either Minnesota, Tennessee, or Arizona, depending on the alloy and temper that's required. All of our steel comes from the U.S. as well, and all of our accessories are U.S. Here, we go down to we have a manual lathe, a surface grinder, a Bridgeport mill, tool and cutter grinder, press, a rod hone that we use for honing the bores or the pinholes of the rocker arms or the bushing IDs to get our fits just right. These are the 2 oldest pieces of equipment in the building, Cincinnati stainless grinders. The bar machine grinds all of the rollers that contact the valve in the rocker arm assembly and also the shafts in the shaft rocker arm assemblies. This machine here only grinds the axle diameters on our trunnions, so this is where the bearing or bushing will ride. This is the part that goes over the stud in the center of the rocker where the whole rocker pivots about. So we've retrofitted this with basically semi-automated. It's got some cams on the back with proximity sensors that will trigger these pneumatic rams to fire at a certain time, and we have a window cut and regulating wheel. So there's a regulating wheel which spins the workpiece and engages it into the grinding wheel. There's a grinding wheel that actually removes the material and does the work. There's a steady rest in the middle, so it'll actually pick up that point on the cam lobe, fire the front ram, force this part into the steady rest through the window in the regulating wheel. It'll grind, and then the other lobe on the cam will hit the other prox sensor, and it will fire the back ram and shoot it down this slide into the rust preventative where it sits until we're ready for that batch to be processed in the next operation, which is normally inspection, then straight into the assembly room because that's the final machining operation that's required. 2 more lathes here, conventional lathes, not like the twin turrets we saw with the rocker arm extrusion. We use these for various purposes, mostly for innovative mounts for their sub-assembly components. Turnbuckles, heim joints, misalignment bushings, solid bushings, bushings for linkages. Again, various materials. That's a 304 stainless, that's a 6061 aluminum. This is a contract manufacturing job we did for another manufacturer. This is all brass. There's a variety of materials that flow through these machines here. And then we have a horizontal mill up against the wall. We have a lot of raw material storage, steel bar stock, and also some of the cold saw cutting operation. And then we have our VF4 cell, which is a series of more Haas vertical mills. VF4s just have a little bit larger travel, either bigger parts or more smaller parts in the same cycle. So that's what happens there, and then we have all of our inventory fabricated mounts as well as all the hardware to kit them with and our bushings here in this area. And then we have basically a 1-piece flow against the wall here where there's a manual press operation. Obviously, as I mentioned, there's different durometer values available for the bushings themselves. So when we inventory them, we don't have any bushings in them yet because this could take 4 different bushings before it becomes the final part number. So this is the most flexible stage of inventory to keep it stocked up in. And then they'll flow down to the packing table, get boxed up, labeled, and out the door. And then inside the room here, more assembly, but this is the rocker arm assembly side of it, press operations, and then a couple manual operations as well. You can see here, this is what our standard rocker arm looks like as far as an empty body. This has already been machined, inspected, deburred, tumbled, and then anodized and laser etched. Obviously it's got a scorpion on it because it's our branded product. 1.83, that's the ratio, so it multiplies the lobe lift on the camshaft by 1.83 times, so it'll open the valve that much. F means forward. This small number down here is a lot number that ties into our manufacturing software. So when this rocker is fully assembled, something happens to it or we want to know, we can look up what raw material lots this came from, what heat treat lots all the steel components came from, what operator ran it through what machine on what day, full traceability for any quality control purposes. And obviously various colors because we do private label manufacturing for other companies as well. So you'll see some with other logos, different colors. We do quite a few different colors in the anodized. The first step we'll do here is we'll press in the push rod seat insert. So these rocker arms, the first thing, and obviously there's various fixtures we'll put in the presses depending on the geometry and the shape of the part. So we'll press in a steel push rod seat insert into that push rod bore, then they'll slide a roller into the roller slot, press the pin in, and then the final press operation is over here. They'll press the trunnion and both bearings in simultaneously. And then they have a clipping table where we install the snap rings or retaining clips manually, and then they check everything for free rotation and defects and function before it goes into the boxes, gets packed, and then gets shipped. So that's basically all of our operations in a nutshell. And the only components we don't make here are the set screws that go into the poly locks for the stud-mounted rocker arms, the bolts that go with the pedestal mount kits, and also the bearings. We get bearings from either Koyo or Universal Bearing, the bronze bushings as well. So those will all be sourced from U.S. sources. Everything else is done 100% here in-house under this roof. So that's everything in a nutshell.
Yes, sir. What about?
No, we sold it when we fully relocated. Correct. This is our only facility.
They
Yes.
moved from Fort Lauderdale.
So you've been here this year. So that's we're wrapped up. That's everything. No, thank you for stopping by. We appreciate it. Nice to